In April of 2026, 4 astronauts became the first human beings in more than 50 years to lay eyes on the far side of the moon, traveling farther from Earth than any crewed spacecraft in history, farther even than the Apollo astronauts ever went. And while the entire world watched that historic flyby unfold, a separate group of scientists, working quietly with data gathered by a robotic spacecraft that has been circling the moon for nearly 17 years, was busy overturning a widely accepted assumption about one of the most important resources hiding on the lunar surface, ancient reserves of frozen water that may hold the key to humanity's entire future on the moon, and possibly the answer to a question scientists have been unable to solve about our own planet. This is the real story of what Artemis II actually accomplished, what scientists studying the moon in parallel with that mission have genuinely discovered, and why the true secret hiding at the lunar poles turned out to be considerably stranger and considerably more useful than anyone expected. To understand why this moment matters so much, you first need to understand what Artemis II actually was, and how significant its achievement genuinely is within the broader context of human spaceflight. Launched in late March of 2026, Artemis II carried 4 astronauts on a mission specifically designed to test the Orion spacecraft and its life support systems on a real, crewed journey around the moon, a critical validation flight paving the way for Artemis III, currently planned for no earlier than mid-2027, which aims to land astronauts near the lunar South Pole for the first time since the final Apollo mission in 1972. Artemis II did not land on the moon. Its mission profile called for a free return trajectory, sending the crew swinging around the far side of the moon before using the moon's own gravity to sling them back toward Earth, a maneuver that carried the astronauts farther from our own planet than any human beings have ever traveled before, surpassing even the distance records set more than half a century earlier during the Apollo program. NASA has described this mission explicitly as America's first crewed lunar flyby in 50 years, and for the first time since the Apollo era, human eyes directly observed the moon's far side, the hemisphere permanently facing away from Earth, a side of our own natural satellite most people have only ever seen in photographs taken by robotic spacecraft. During that historic flyby, the Artemis II crew paid close attention to a specific, scientifically significant region called the Oriental Basin, an enormous impact structure on the moon's far side, whose subsurface composition has been mapped in detail using gravitational data collected by NASA's earlier gravity recovery and interior laboratory mission, commonly known as GRAIL. Robin George Andrews, a science journalist covering the mission for Scientific American, described the broader scientific ambition driving this entire era of lunar exploration in a single, direct statement, noting that if NASA's ambitious lunar exploration plans succeed, scientists intend to cover the moon with a genuinely comprehensive network of instruments and sensors, finally answering several long-standing questions about the inner solar system that have remained unresolved for decades. Chief among those long-standing questions, and the one drawing the most sustained scientific attention right now, involves water, specifically the ancient frozen reserves of water ice believed to be hiding within permanently shadowed craters near the lunar South Pole, regions so deeply shadowed that direct sunlight has not touched their floors in what scientists have long assumed was billions of years. This is precisely the region NASA has selected as the target for Artemis III's planned crewed landing, and for good reason. Confirmed water ice at the lunar poles represents what planetary scientists routinely describe as one of the single most valuable resources available anywhere off Earth. Water that could theoretically be purified for drinking, split into breathable oxygen, or processed into rocket fuel, potentially transforming the moon from a simple destination into a genuine refueling and resupply outpost for deeper missions heading toward Mars and beyond. The idea that ice might exist at the lunar poles is not new. Spaceflight pioneer Robert Goddard first proposed the possibility more than a century ago, and indirect evidence supporting that hypothesis has been steadily accumulating for roughly the past 2 decades. NASA formally confirmed the presence of polar ice back in 2009, and additional research, including a landmark 2021 study using NASA's SOFIA Airborne Observatory, has since confirmed the presence of actual molecular water even in sunlit regions of the lunar surface, not just the permanently shadowed craters near the poles. But confirming that ice exists is a considerably different question from understanding exactly how old it is, how it actually got there, and where scientists should focus their limited exploration efforts to find the richest, most accessible, most scientifically valuable deposits. This is precisely the question a team of researchers at the Weizmann Institute of Science set out to answer, publishing their findings just days after Artemis II's historic launch, in research that fundamentally challenged assumptions scientists had held about specific lunar craters for years. Shackleton Crater, located near the lunar South Pole, has long been considered one of the single most promising sites in the entire search for accessible lunar ice, and researchers had generally assumed this crater had remained in permanent shadow. and therefore capable of preserving frozen water for roughly 3.5 billion years, essentially since not long after the moon itself finished forming. The Weitzman team's new analysis revealed something genuinely surprising. Shackleton Crater, they found, only actually became a true cold trap, a region cold and dark enough to reliably preserve ice over long periods. Around 500 million years ago, a dramatically more recent transition than scientists had previously assumed, driven by subtle, gradual shifts in the moon's own orientation and the specific geometry of its permanently shadowed regions over time. This finding carries genuine practical significance for how researchers actually think about where to look for the most valuable, most scientifically informative ice deposits on the moon. If a crater like Shackleton has only functioned as a genuine cold trap for a mere 500 million years, rather than the multi-billion-year timeframe previously assumed, that fundamentally changes expectations about how much ice that specific location could realistically have accumulated. And more broadly, it demonstrates that the lunar poles are considerably more dynamic and more geologically active in this specific, subtle sense than the popular image of an ancient, frozen, unchanging surface generally suggests. Complementing this specific finding, separate research analyzing data gathered by NASA's Lunar Reconnaissance Orbiter, a robotic spacecraft that has been continuously mapping the moon's surface since 2009, now nearly 17 years of continuous operation, suggests that lunar ice has likely been gradually accumulating for somewhere around 1.5 billion years, a finding published in the journal Nature Astronomy that helps refine exactly which specific shadowed regions are most likely to contain the deepest, most scientifically valuable, and most practically useful ice reserves. Here is where this entire scientific effort connects to a genuinely bigger question, one that extends well beyond simply finding water for future astronauts to use. While scientists still do not have a fully settled answer to one of the more fundamental questions about our own planet, exactly where Earth's own water actually came from in the first place. Two primary competing theories have dominated this debate for years. Either ice-rich comets delivered the bulk of Earth's water during the early chaotic period of solar system formation, or considerably drier asteroids did the job instead, carrying smaller amounts of water bound up within their mineral structure rather than as pure ice. Geochemical analysis of meteorites, combined with detailed studies of the chemical composition of Earth's own oceans, has generally pointed toward asteroids as the more likely primary source. But researchers studying this question have been direct in stating that the case remains far from conclusively closed. This is precisely why the moon offers such a genuinely unique scientific opportunity. Unlike Earth, whose surface has been continuously reshaped by weather, plate tectonics, and billions of years of active geology, much of the lunar surface has remained essentially frozen in time, undisturbed for billions of years, preserving a far more pristine physical record of the early solar system than anything remaining on Earth itself. By carefully studying the specific chemical composition and isotopic signatures of the ice actually preserved within these permanently shadowed lunar craters, researchers hope to determine whether that ice more closely matches the chemical fingerprint of cometary ice or asteroid-derived water, potentially providing crucial supporting evidence for finally resolving this exact same question about our own planet's watery origins. This is exactly the kind of direct, ground truth investigation Artemis III is specifically being designed to support. Russell, a NASA researcher directly involved in planning these future surface missions, has described one of the key instruments planned for an upcoming crewed mission, called the Lunar Dielectric Analyzer, a device specifically capable of detecting electrical currents within the lunar ground itself, currents whose specific patterns can reveal the presence and physical state of ice hidden beneath the surface. Russell explained plainly that this particular instrument will help researchers understand not just where water exists on the moon, but the specific physical form that water actually takes. Information that orbital spacecraft like Lunar Reconnaissance Orbiter, however capable, simply cannot gather with the same precision as an instrument placed directly on the ground. NASA's next-generation lunar terrain vehicle, an updated moon buggy designed to operate either under direct astronaut control or through fully autonomous navigation, is expected to conduct similar ground-based investigations, extending the reach of human and robotic explorers considerably farther across the lunar surface than any previous crewed mission has ever managed. It is worth being honest and precise about exactly what Artemis itself did and did not directly accomplish scientifically, since that precision matters for understanding this story accurately rather than overstating the mission's specific role. Artemis II was fundamentally a crewed test flight, validating the Orion spacecraft systems and demonstrating that astronauts could safely travel to the moon and back using this new generation of hardware, and its historic flyby did not involve landing on the surface or directly deploying scientific instruments capable of sampling lunar ice. The specific scientific findings regarding Shackleton Crater's surprisingly recent transformation into a genuine cold trap, and the broader estimate of roughly 1.5 billion years of accumulated lunar ice, emerged from parallel research efforts, analysis of existing satellite data, and dedicated new modeling work that happened to be published in the same general window as Artemis II's historic launch, rather than data gathered directly by the Artemis II crew themselves. What Artemis II genuinely accomplished was re-establishing crude human presence in lunar space for the first time in over 50 years, setting a new distance record for human spaceflight and providing the essential technical validation needed before NASA commits astronauts to an actual landing near the lunar South Pole, exactly the region where these separately conducted scientific studies suggest the most scientifically valuable ice deposits are most likely to be found. Taken together, though, the timing genuinely matters and connects these efforts in a way that goes beyond simple coincidence. Humanity is, right now, in the middle of 2026, actively building toward its first crewed return to the lunar surface in over half a century, specifically targeting the exact region where scientists have just revised their understanding of how, when, and where the moon's ancient ice reserves actually formed and accumulated. Every new finding about the true age and distribution of that ice directly informs where NASA ultimately decides to send Artemis III's crew. Every future measurement those astronauts eventually take on the ground will, in turn, help settle genuinely fundamental questions, not just about the moon itself, but about the origin of water on Earth, and by extension, the basic conditions that made life on our own planet possible in the first place. So here is the honest, complete picture of what is actually happening across this remarkable interconnected chapter of lunar exploration. Artemis II carried 4 astronauts farther from Earth than any human beings have ever traveled, giving the world its first direct human eyes on the moon's far side in over 50 years. At almost exactly the same time, separate teams of scientists revealed that one of the moon's most promising ice-bearing craters is considerably younger, in terms of how long it has actually functioned as a genuine cold trap than anyone previously assumed, while other researchers refined estimates suggesting lunar ice has been slowly accumulating for roughly 1.5 billion years. Together, these efforts are steadily building toward Artemis III's planned crewed landing at the lunar South Pole, a mission that may finally place human hands directly on ice that has been hiding in permanent darkness for a genuinely staggering span of time, ice that could ultimately help answer one of the biggest remaining questions about the origin of water on Earth itself. If you want to follow what Artemis III's astronauts actually find when they finally reach the lunar South Pole, subscribe and turn on notifications, because the answers hiding in that ancient frozen darkness could reshape our understanding of the moon and of our own planet's origins all at once.